Good evening, everyone. This is Physics 28, and I'm glad that you have all these nice students on H. Fun, Elizabeth, Kirk, Nikki, Rurika, Simasuk. Glad to have you all, and here is my face. Okay, so you know how this works. You ask me question, and by the way, it's all being taped, and I will export that to the classroom later. So you ask me whatever. Um, and you need to have a microphone, or you can type. You can type. Where do I type? uh, oh yeah, there is a, if you go with your cursor down, there is a little symbol of chat. You click on it and then you can start sending messages. So I have Elizabeth Mello. Hi everyone. Hi Elizabeth. Nikki, hi. Elizabeth Mello said, hi, here. Okay, got it. Okay, and the floor is open. You can type. If you don't have a mic in your computer, you can type whatever you need. Simarsuk. I didn't. So to type, you take the cursor down to the bottom of your chat screen. There is a symbol chat in there. You click on it and you should be able to. Okay, I didn't understand this problem from the homework. Dart is drawing at a dartboard. Okay, let's work on that. Okay. Okay, now let me bring it to the screen. I have to learn to navigate through all these buttons and be efficient. Okay, let me share a white screen here. Can you all see this? I think you can, huh? This is the problem. Annotate. Okay. So you all can see what I just put in the screen, right? Okay, this is a question. A dart is thrown at a dartboard that is 3.74 meters away. When the dart is released at the same height as the center of the dartboard, it hits the center in 0.706 seconds. At what angle relative to the floor was the dart thrown? Okay, so look at this. So you have a dart board. So a dart board is something like this, right? I mean, not exactly like that, but very well done. And what I'm going to do, I'm going to rotate this so that you see it like this. That's the dartboard I seen from the side. And here's the center, the bullseye, right? And let's do a horizontal like that. Block. Okay, here's the thing. So you're going to throw a dart. You're going to throw a dart. So if you, oh, sorry, I don't know why I'm doing this. Hey, what is that? Why am I doing this? Oh, shoot. Why this freaking thing? I'm sorry. I didn't mean that. Okay, it went away. I put an eraser. Annotate. Okay, my dart looks like a bird. So if you send the dart because of what's going on? Is there a carnival going on out there? So if you throw the dart with this angle, which means parallel to the horizontal, here's what's going to happen with the dart. It's going to go like this. Kind of this broken line is going to be a parabola. It's going to miss your dart. Of course, it's not going to be as great as this one, right? But that's what's going to happen, which means to allow for the dart to hit the bullseye, you have to throw at an angle. So here is your initial velocity, and the angle has to be such that when you throw, the thing goes up and kaboom, hits the bullseye right there, like this. Does that make sense? So this is the angle in which you throw the dart. So what do you know? What is being given is being given this distance, right? 3.74 meters away, and it's given the time that it takes the dart to hit the bullseyes, which is that much. So given information, this and that. Now, very important, you don't have air resistance. If you don't have air resistance, you know the acceleration in there is 9.81, sorry, meters per square second. So there is only one, and it's negative, pointing down, no drag forces. So how do you solve this problem? You decompose your problem in two components. One that has to do with x, and another one that has to do with y, right? But before you start this type of problem, this is very important. You have to, because see, it's what do you want to solve for? You want to solve for the angle. What is the angle theta? Release this dart so the dart can hit the bullseyes. Remember, if you throw horizontally, it's going to miss the bullseyes. So you have to throw at an angle. So you want to find the angle. Angle is your unknown quantity. So then you have an analysis to do with your velocity. You have your velocity initial going like this, and you have an angle theta right here, and it means you have your V naught in the x direction, and that is equal to V naught cosine of that angle theta, and you have a V naught in the y direction. In this case, a positive number, right? Positive number, which is V naught sine of that angle. You have to be willing to do this analysis as the first thing in your problem, if the problem is a projectile motion problem. So x component, the only equation you have is x is equal V naught x times time. And you start smiling, right? You put yourself in a big smile because look at this. You have x and you have time. So you can calculate your V naught x. Isn't that cool? That's really cool. So then let's do that. So x, 3.74 is equal to V naught x times the time, is 0.706. And then we can calculate your V naught x. It's 3.74 divided by 0.706. This is in meters per second. Okay? So you have your V naught x. And you know that your V naught x, whatever number you got from this ratio, is equal to the initial velocity in meters per second times cosine of that angle, and you want to find the angle, basically. Okay? Now, which means you can write your V naught here as Vx naught whatever you got from here, divided by cosine of theta. Okay. Now let's go to the y component. So y component, one equation that involves time and position is y. There is a phrase of a background sound going on. Can somebody mute the phone? Could it be unfun? Unless you want to say something. You see whoever. Yeah, I think it was unfun. Okay, better. So y minus y naught is equal v naught in y t minus half g, which is 9.8 t squared, right? T squared. Separate that. Now, look at this. What is your initial position in y? Is here. So your y naught is 0. It's at level. And what is your final position? Bullseye. So your y final is 0 meters. You hit the bullseye. So because the dart is released at the same height as the center of the dartboard, right? It's not, is the same level. So which means y minus y naught is 0 minus 0. And what is v naught yt? V naught yt is v naught sine theta minus 4.9 t squared. Now, look what this allows you to determine. This allows you to determine v naught sine theta. Why is that? Well, because I have t, and I have t squared. Wait a second, my marker. Okay. You have t and you have t squared, so you can find your, oh Jesus. You can find your v naught sine theta. Your v naught sine theta, and unless this is too messy, is equal to 4.9 times t squared, and t is 0.706 squared, divided by t, which is 0.706. So this is square. So 1 square go away. So you have your v naught sine theta. But let me move down so I can. Oh, I can move down. So are you all there? So v naught sine theta is a number. But what is v naught? V naught is v naught x divided by cosine theta. So look what I got. I'm going to write here. Can I write there? Yeah, I can. Look at this. So v naught sine theta is equal v naught, which is vx naught divided by cosine theta times sine theta. So this quantity here is your v naught. Sine theta is sine theta. This is equal to this number right here. V naught sine theta is equal to 4.9 times 0.706. I already canceled one of it. And V naught x, I know, is calculated here. It's 3.74 divided by 0.76. Sine theta over cosine theta is tangent theta. And this is equal to 4.9 times 0.706. And then we can calculate tangent theta. We can calculate tangent theta. So tangent theta is equal to a number, which is 4.9 times 0.706 divided by 3.74 times 0.706. And then you can find your angle. It's kind of a messy here, but I hope you follow. Any question? Do you want me to repeat anything here? Now you have to use your microphone or I can't see it. Unless I stop sharing and then I can see if you have any question there. So Simmersuk, how is it? Did you get it? Did you get it? Professor Frozen, ha ha ha, can you put the problem back up, please? Did you understand now? Yeah, I got it, thanks. I'm still writing it down. Okay, I can put it back, but remember, I will upload all of that as soon as we finish this conversation. But yeah, I can go back there. Oh, I don't know if I can. I think if I share the screen, it's gonna come all white. Oh, I have to do all over again. Oh my God, I'm not gonna do it. Forget it. You miss, you lose. Sorry about that. So let me go back to the chat room. Quiz number 2. Okay, good, Elizabeth. Now, Justin Lee, can you go over the quiz number 2? Which quiz number 2? Do you have it? Do you have it in your computer? Which one is this? Oh, the one I sent it to all of you? Oh, yeah. Let me see if I can find it here. Wait a second. Find. Okay. Open recent file, class 0 studies, view all recent files. Open. And I go to Physics 2A. Quiz number 2. What is quiz number 2? Quiz number 2. Open. Okay, so I have quiz number 2. Let me see if I can share the screen now. Share the screen, quiz number 2. Okay, there you go. That's quiz number 2. Now you have to use your microphone because I can't see you typing now. So can you tell me what you need me to do? Are you there? Hello? Hello? I have Ananda, I have Cindy, David, Nikki, Elizabeth, Kirk, Raman, Anand, Simerson, Julie. Oh, Julie, you made it.
Hi.
Hi. How was your drive? No accidents, huh?
I'm driving.
Oh, you're driving. You shut this down. I need you in class tomorrow. I don't want to talk to you.
Well, you don't have to.
No, I don't want to talk to you. Just yeah. You can watch later. So I need.
I was just.
Yeah. Go ahead. Well, I think I lost you. Somebody asked me to open the quiz number 2. Here it is, but I need to know. Okay, I can't hear. It might be something bad with the mic. So I'm gonna go back to see what's going on here. Okay. He said he's not going to look at the chat. Everything, yes, yes. Okay, yes, we are here. Unfun to everyone here. Justin, everything. He said he's not going to look at the chat. AW RIP. This looks like a crazy communication. I'm not understanding what's going on. Are you guys writing in English? So is there any... Oh, I have a message. What is the message? Please don't kill me for asking. No, I'm not kill. I'm pretty much far away from you, so I can't kill you. I think Justin wants you to go over everything? You're crazy. How can I go over everything? I mean, it can't be a class. This is not a class. You have to come with specific questions. I mean, you guys, you young people, don't like to be told what to do, right? And have some professor going there and write down things in a board and bore you to death. You don't want that. You have to go ahead and ask specific questions. That's what you do in a text freaking message. You put a sentence, and there is a universe of communication in there. But can I do everything? No, I cannot. I cannot do everything. But you did last time. But I'm lost. I cannot find you. I'm not God. I really cannot find you. You have to be specific, just saying. This chat room can only work if you are specific. I can open... why don't you go over to your PDF and ask specifically for me to do something? There is no time for me to go everything. Oh, freak. Let me go everything. Let me do everything. I'm so bad. Sometimes I think I should go back to the wound of my mother. Okay, where is the... No, that's not it. I can't even find my PDF. Okay, just a second. I think that's the one. Adobe. Okay. Okay, so I'm not annotate. Somebody with a microphone tell me to stop, right? Because I can see the chat room for some reason. When I share my screen, I don't see what you guys are talking, unless somebody with a microphone can intermediate and stop me. Can somebody, Elizabeth? Can you? Because I know you are there and you have a nice. Oh, Nikki, can you please be administrator here and keep one eye on what's going on in the chat room, and at the same time see if somebody has a question? Can you do that?
Okay.
Yeah, so you have your microphone on, that's perfect, and then you can help me. So I'm gonna go over the entire quiz for Justin. I think Justin was the one asking. But Nick, you have to keep your microphone on. No, you don't. Only if somebody asks a question. Okay, let me go through that. According to Newton, oh, this one you don't need it for tomorrow. Newton's second law is not tomorrow. Free body diagram is not tomorrow. Okay, Adam. Adam drops the ball from rest from the top floor of a building. At the same time, Bob throws a ball horizontally from the same location. Which ball hits the ground first? Neglect any air resistance. So look at this. The ball is dropped from rest, right? Which means the initial velocity in y for Adam is 0. Now look at Bob. Bob throws the ball horizontally, which means the initial velocity in y for Bob is also 0. So when you write down your equation in y for both of them, Adam and Bob, you have y minus y naught, which is the height of the building, is equal initial velocity times time. And if I start annotating, I cannot do that. See if I can. Right. So for Bob and Adam, y minus y naught is equal v naught yt minus half gt squared. So for both of them, this is the height of the building, right? Whatever number of meters that is. And for both of them, the initial velocity is 0. For Adam, because he drops the ball from rest. And for Bob, because different from the previous problem I just did, the ball is thrown with an initial velocity that is perpendicular to the y-axis, like this. So the initial velocity in y for Bob is 0. So this quantity is 0, which means the time for both of them will depend on the height of the building and the value of g, right? And that's it. So this is pretty much the time is the same. Okay, can I move on? Can I go down? Let me see if I can. Okay. The second one, an object. Annotate. Comment. How do I do that? Oh, there you go. Annotate. Okay. An object travels with a constant acceleration for 10 seconds. So the time is given and the acceleration is constant. The vectors in the figure below represent the final and initial velocity to determine the average acceleration. So the average acceleration, the only thing you need to do is to use the concept of average acceleration, which is, oh, it got frozen. Why it got frozen? Your high CPU usage is affecting the meeting quality. Okay. I'm having problem. I cannot write anything. I got a frozen. Hey, what's going on? Come on. People will see you. For some reason, my screen is frozen.
Professor?
Yeah.
So for question number 3, Elizabeth said that you said time and height, but in the choices it doesn't say so. Like for the answers for number 3.
So Justin was asking what the answer was, and I said
the
you
answer.
said height and
It depends on, okay, the answer. It depends on how fast the ball falls. No.
Okay.
It depends on how fast the ball falls when Adam drops. But Adam drops the fall from rest. Right? So this makes no sense because he drops from rest. B, Adam's ball, no. They both hit the ground at the same time. So C, A, B, B, this is wrong. This should be C. Right, the third option. The fourth option, it depends on how fast Bob throws the ball. No, it doesn't. And D, Bob's ball. No, so it should be the third option, which is the second B. They both hit the ground at the same time. Okay? So in this problem, for some reason, I'm not being able to annotate, and I don't know why. It's something with my CPU and the use of this tablet. I have to delete a lot of videos that I put in here, so I apologize for that. So I'm just gonna say it. So you use the definition. Let me see one thing here if I can do. You use the definition of acceleration, and acceleration is the final velocity minus the initial velocity divided by the time given, and the time given is 10 seconds. So what you need to do is to find the value of your VF. So let me see now if I can write it down. something with my pen because I can't use the cursor. So VF, I'm using a very bad way of communicating here. VF is 20 cosine. I'm not using my tablet now, so it's taking forever here. V is 20 cosine of 30 in the x direction, right? Plus 20 sine of 30 in the y direction. So that is how you write your velocity in vector components. Now the initial velocity is written as, so in x, vi in x gives a vector that is positive, as you can see. And it is given by what is the value of vi? Is it given? You guys are in the way. Okay, there you go. It is 20 times cosine of the angle between the vector and the axis. So the angle is 60. The angle is 60. So cosine of 60 in the x direction. And I apologize for the way I'm writing. And look at this, but V initial, when it projects in the y direction, it goes in a direction that is negative. So minus, and this is for Julie Lee.
Yes.
Julie Lee, as long as you know the angle and you know in which direction the vector is pointing, you don't need to plug negative numbers or negative angles on your projection. So you know it's negative, right? The vector is pointing negative. So you put a negative there and forget about it. 20 cosine of that angle is 30. Cosine of 30 in the y direction. Or sine of 60, whatever you want to write. Now, the definition of acceleration as being final velocity, final minus initial velocity, right? Final minus initial divided by the time, which is 10. Then what you do, you subtract those two vectors. You subtract VF minus VI. And I will say it. So it's 20 cosine of 30 minus 20 cosine of 60 in the x direction, plus 20 sine of 30 minus 20 cosine of 30 in the y direction. So it becomes positive. And that's how you do. Again, divided by 10. So your final average acceleration would be 20 cosine of 30 minus 20 cosine of 60 plus 20 cosine of 20 sine of 30 minus 20 cosine of 30. Does that make sense?
Professor, I have a question.
Yeah.
For acceleration, the equation on the bottom, what does that say? What is that symbol under V final minus
Oh,
V
it's the
initial?
10 seconds. I'm
10
not
seconds.
being able to write with my stylus pen. For some reason, it's all frozen. But it's,
Okay, thank you.
it's this 10 seconds. 10. This is a number 1.
So pretty much
How come you can't see
all
this?
over time.
Yeah. Final velocity minus initial velocity divided by the timing in seconds of that time interval. Yeah. Okay.
Thank you.
You're welcome. Let me see. Oh, we have a music.
I was wondering, did you say like instead of the negative 12 cos 30 from cos 60 and the V and idle, do you say we can use sine 60 as well?
Yeah, you could. See, you could you could write sine of 60. Like I wrote cosine of 60, right? Cosine of 60, because I'm projecting along the x direction, the angle between the vector and the x direction is 60. Cosine of 60. And here, I could write sine of 60. Sine of 60. And that would be its projection in y, as long as I put a negative sign. Now, cosine of 30 is the same thing, the same number as sine of 60. That's why you can do that. So what you do when you project a vector onto some axis, if you know the angle between the vector and the axis, it's cosine of that angle, because you are pretty much targeting the adjacent side of that angle. So here you are trying to project here, the angle is 60 degrees. So you could project y in the v initial in y by saying, well, that's cosine of 30, right? Or sine of 60. It's basically the same. Good enough? Okay, let's go to the next one. If I can, yes. Determine the net force. No, forget about net force. Oh, we will learn that. So net force, was a simple problem. So the net force is equal to the mass of the object, which we are learning in the lab now, times the acceleration you got before. That was a simple question. Okay, number 6. A soccer ball is kicked with a certain initial velocity at a given angle above horizontal. What are the velocity vectors of the ball when it is 1 meter above the ground level? Assume the ball was on the floor. So here it is. So let's do a little drawing on it. Let's see if I can use my tablet now. What the heck are you doing? Yeah, it's not responding. Let's see if I can connect with a cable. Should be more specific. It could be my computer is not accepting that. Okay, let me try that one. Okay. Yeah, funny, my stylus is not working. I don't know why, so I'm taking this out. All right, so let's do this one. I have to do with my hand here. It's not the best option. Okay, so this is the floor, perfectly horizontal, as you can see. And then you have a soccer ball that is thrown with a initial velocity, 24 meters per second, okay? And the angle is given 30 degrees. 30 degrees. Now, when you throw this ball, when you kick this ball, it's gonna go like this. Projectile motion, yeah, 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 yeah. And what are the velocity vectors? So there are two. When it is 1 meter above the ground. So this point, right? It is 1 meter above the ground. But look at this. This point also is 1 meter above the ground. So there are two velocity vectors. That's the whole thing. So you have one velocity vector when the ball is moving up to its highest point, and you have another velocity vector when the ball is going down. So it's go like this, and then fall. So here reach 1 meter, and then it goes down. No, 1 meter keeps going up, and then it goes down another meter there, right? So first thing you do, what's the first thing you do? You guys tell me. I mean, you have this problem. What's the first thing to do?
Analyze the initial condition.
There you go. For what? For your velocity. So you have a velocity vector that is like this. 24. So what do you need? You need your v naught x, and you need a positive, look at that, beautiful, v naught y. So this is 24 sine of 30, and this v naught x, to write is horrible here, is 24 cosine of 30. So this angle here is 30 degrees.
I have a question.
Yes. Who's this?
Is the x always cosine and the y?
No. Let's say that I give an angle of 30 degrees with respect to the vertical, respect to the person who is kicking. Some person, look at this. Who asked the question? Elizabeth?
Yeah, I did.
Hey, Elizabeth Mello, that's you right here. You know,
Okay.
with a happy face. And then you kick the ball. So let's say I give you an angle that is 70 degrees with respect to you. So you're not going to say v naught x is 24 cosine of 70. It's not. Because the angle that it makes with the x-axis would be 20. And then you would write 24 cosine of 20. You have always to see which angle the vector makes with the axis you want to project. Because that's the angle you use in your projection. Now, the adjacent side is this one. Right? That's why we are using cosine. And we are using sine because it's the opposite side of this angle. That's why it goes in sine. Okay? So the first thing you do is this analysis. Once you've done that, you go to your table. And the table is, I have your x component, I have a y component. In x component, what you got is, well, x positioned at any time is equal to 24 cosine of 30, I can't write, it's so bad here, cosine of 30 times the time, whatever time that is, okay? And in y direction, you have y at any position minus y naught, the initial position, is equal to v naught y, and then you write your 24 sine of 30, 24 sine of 30 times the time it takes to go from here to this first point, and also the time that it goes to the second point. I think in our analysis we are going to determine 2 times. One when the ball is moving up to its highest point, and another time when the ball is 1 meter but going down in its curve, minus half, 9.8 times square. So, but then you say, okay, what is the y? Y is 1. And what is y naught? You tell me. What is the y naught?
0.
0. So you have 1 minus 0 is equal some number times t and another number t squared. So you have an equation, second degree equation, and I saw some of you don't know how to solve second degree equation. So this is supposed to be given. If you forget how to do it, you have to ask me for the equation if I don't give you. So you have an equation in second degree, not in x, right, but in t, t squared plus bt plus c equals 0. And that allows you to calculate 2 times. Because the first time is when the ball is going up. The second time is when the ball is going down. So once you have that time, your v naught x is the same all over. So we have a v naught x here, v naught x, which is the same as in here. I mean, v naught x does not change. It's always the same. V naught x doesn't change. But v naught y change. Your v naught y here is a component that is y, is positive. And your v naught y here is a component that is negative. So v naught y is going to be given by v naught, I'm sorry, your v, I'm getting tired. Your vy is equal your, and I can't write well here, v naught y minus 9.8, we have to use the equation of motion, times t. So once you find time in the second degree equation, you plug it in here, and then you can find your y component, right? Because you have your v naught y. And then the second time you plug it in here, you have this component given. And believe me, this first component in y will be a positive velocity in y because it's going up. The second one will be negative. Got it? Okay. And I'm gonna clear this so I can go to the next one. Clear all drawing. Yeah. Why can't I? Oh, is this the last one? Was that the last one? Let me try.
No, there's one more
There's
still.
one more. For some reason, I couldn't move. I thought, okay, now I can. On a beautiful sunny morning, Taffy Nguyen leaves home and bikes 50 kilometers, heading 30 degrees north of east. When she stops for a water break, she then turns due south and bikes for another 25 kilometers scenery route to visit her aunt Kathy. How far from home does her aunt live? Okay, so X and Y. And so this is displacement. Imagine this is a Google map and you are seeing north and east, right? And then she goes a displacement of 50 kilometers. 50 kilometers with an angle of 30 degrees. And you guys have to be able to read this north of east. North of east, because this is north, this is east, right? And this is south, and this is west. And then she stops for a water break, and then she turns due south. So from here, she goes due south like this. And then she bikes for another 25 kilometers. 25 kilometers. How far from home does her aunt live? So we want to find if you call this vector A vector, and if you call this 25 kilometers a B vector, so you want to find the final displacement, you want to find the D displacement vector, D. So D is equal to A vector plus the B vector, Okay. Now, the best way to solve this type of problems is you go, okay, my A vector, I'm going to write as a function of its coordinate, its Cartesian components is equal to, you tell me, 50. What is the A projected in X? Is 50 what?
So you wouldn't use the Pythagorean theorem on this?
No, how can? We don't know where this 25 ends. You don't know. You have no idea. You could write, for all I know, she bikes, where's the annotated? The 25 kilometers could end right here. So how are you going to write a Pythagoras theorem here? You don't know.
Okay.
Your Pythagoras theorem, you could, if you know what this is and what this is. And then it's the square of this component, this side, plus the square of this side.
Got it.
Square root of that, right? But we don't know. I mean, when you're setting up the problem, you don't know where to stop with this vector. I stopped here, right? But I could have stopped there. I don't know where to stop. So the only way to do and avoid some misleading solutions with the geometric method, which is the one I'm doing in the sketch, is to really work on the Cartesian projection. So A projected in X is 50, follow me here, cosine of 30 in the X direction, plus 50 sine of 30 in the Y direction. And what is your B vector? My B vector doesn't have a component in X because Taffy, she turns due south, right? Due south. So it doesn't have a little puny component in X, is 0. But she has a negative component in the south direction, which is 25 in the Y direction. That's it. So when you add these two vectors, it gives you the D vector, which you want to find, and that is equal to, erase this thing here.
And why is the X 0? Is it because it's not moving anywhere? It's just going down on the Y-axis?
Because it is said that Taffy, she moved straight south, due south.
So she didn't move on the X-axis, she just moved on the Y.
Exactly. So she didn't go like this. You see that?
Mm-hmm.
If she had moved like that, she would have a Y component plus an X component. So this X component does not exist. It's not part of the problem. Got it?
Yep.
Okay. So then when you add those two vectors, then you got 50 cosine of 30 in the X direction plus in the Y direction is 50 sine of 30. But sine of 30 is 25. I'm sorry, I'm going ahead. Sine of 30 is half. So half times 50 is 25. So 25 is this thing here. Minus 25 in the Y direction. So look what happened. It doesn't have a projection in Y. So which means this vector, let me annotate in a different color if I can. Can I change color? Spotlight, draw, redo clear. Can I take a different color? Let's see if I can. So the final vector, no, I cannot. It stops right here. Stop right here in the x-axis. So the d is primarily 50 cosine 30. Is this thing over here? Stop there. So your d vector is this one over here. This is your d vector. So how far from home does her aunt live? It lives 50 kilometers cosine of 30, basically. Due east. Due east.
So do we need to find the answer to that, or can we leave it like that?
We leave it like that. That's it.
Leave it like that? Okay.
Yeah, go to the cheering crowd. That's it. It's funny, I can't move. Oh, now I can. For an extra bonus, determine the direction of Taft's aunt home with respect to her. Well, it's 0. It's due east, right? So the size of the vector is 50 cosine of 30, and she is due east exactly, or in the x direction. That's how you would do it. Okay, so that was the exam that I gave on summer. So did you guys work on your class sheet, the one I sent? I saw some of you working on it. That was good. Should do that. Oh, good. Mr. Kirk, are you all right? Man, there's a lot of you. Don't you guys have anything better to do?
So, Professor, is the displacement, it's always the origin and then the geometric head, is that correct?
The displacement with respect to the origin, if that is being asked, yes. So let's say I have in this case, right? So there was you have your Cartesian axis, and this lady moves like this, and then like that. So the displacement with respect to the origin is this vector here. That's your displacement vector.
That's the displacement. Okay.
Yeah, but let's say you have a different situation. You have a like a male person, like a male lady, and then she drives her car. This is north, east, south, and west. And then she leaves the post office and goes north. And then she turns around, she go north of east, right? And then she goes due south, and then she goes west for several miles. And then she finished her route right here, point P. And then I ask you, what is her final displacement with respect to the origin? Here it is. That's what it is.
Okay.
So that's the displacement. So how do you find this number in meters or miles? Well, this is a more kind of a challenging problem, but you have to write your vector A, vector B, vector C, and vector E as Cartesian components, right? And then add them like we did in the previous problem, and then you'd have an X projection of that vector D plus a Y projection of that vector D. We call this dx, and this your dy. And your displacement vector would be the Pythagoreans, like you said in the beginning, of those two components. Your dx squared plus your dy squared. So here is your dx squared, and here's your dy squared in this case, in this particular case.
Yeah, folks.
Good enough?
Yeah, and then I had a last question earlier when you were saying about a lot of people missed on plugging in like a second equation for time. So if we need to find time and we use that y equation, we just plug in that ax squared minus bxc.
In
Is that
some
correct?
cases, not in all cases, you are finding time in the x projection. You could find time in the y projection. You could find time in the x projection. In projectile motion, the x component is this x. I apologize for this bad writing, but that's what I got now. Is your v naught x versus time.
Yeah, I got that.
Right? So let's say a situation, I give you a situation like this. Your V naught is given, right? And the angle is also given.
Yep.
So you know this quantity here. And I tell you that once the ball is sent, it falls 700 meters away. So you have x. You have x. So because of all this given information, I give you the initial velocity, I give you the angle, and I give the range in which the ball moves. You can find time.
Yeah, but I want to know, when do I use that other equation?
The one y minus y naught?
The one that's the ax2 minus bx.
Yeah. So let's
That's
say
what I want to know
if you
because
have
I didn't use it last time. So.
yeah, let me clear this. I don't remember exactly what values you would have in that equation, but let's say that after you've done all your analysis, you get to a point like this, 4.9, and I'm making up the numbers, okay? 4.9 t squared minus 3.2 t plus or minus 3 is equal to 0. Let's say you get yourself in an equation like that. So how do you solve? And I had 2 or 3 students, they try to factor and find a solution. And they clearly they didn't know how to solve a quadratic equation. How do you find solutions to that? So here's what you do. So this is your coefficient A. Here's your coefficient B. And here's your coefficient C. So T, the solution, is equal to, and then you put a bar like this, is equal to negative of your B coefficient plus or minus, that's the standard solution, plus or minus the square root of B squared minus 4 times the coefficient A times the coefficient C divided by 2 times A. That's how you solve. So let's say you did the physics problem and you find yourself in a quadratic equation like that. How do you solve for T? Well, T is going to be, then you look at your equation and you just replace it by these values. Negative B. Negative B is negative of negative 3.2. So you know that you're going to get yourself on a positive 3.2, right? Because negative is positive. Plus or minus square root of B squared. So when you take your negative 3.2 and square, it's the same thing as 3.2 square. So you're going to take this negative 3.2 and square minus 4 times the coefficient A times 4.9 times the coefficient c in my example is a -3. A -3. All of that divided by 2 times a, which is 4.9. So that's how you solve your quadratic equation. And you have to be careful here because see, this negative with this negative over here becomes positive. So you add whatever is in the argument of this quadratic equation, and then you can solve your problem. So in this case, you have only one time that's going to be, or yeah, it's going to be, yeah, one of the times. You're going to have only one possible time in this quadratic equation. But in the one we just did, you might be able to find two solutions, and both of them are good. Elizabeth, is that okay?
Yeah, when you use this, so when I would use this would be when I couldn't use the x component equation. Is that correct?
Yeah. You are going. You always gonna find a quadratic equation when you are solving in the y projections. In the x projection, you do not have a quadratic equation.
Okay.
Thank you.
Good enough. Okay. All right. Good work. I will be checking my email in about 1 hour before I go to my crib. So if you guys have a quick question, you can send me and I will check. Good enough?
Yeah, thank you.
All right. Good job. Good job. Nikki, thank you for managing this. It's very helpful. And I hope this chat room works for all of you. Okay? Okay, good night. See you mañana. I will upload pretty soon.